welcome to the Tech Talk today. It's a pleasure to introduce Professor Bernstein from University of Zurich. He's a professor at University of Zurich since 6 years, and before did a PhD at MIT. And since about 3 years, he's looking into exploring natural language, also in the context of doing web search using natural language. And so the Tech Talk today is about how to use this language and how to make it really accessible to everybody. And it's a great pleasure to have you here. Okay.
Thank you, Thomas. Thank you very much. It is a great pleasure to be here. The last time I spent a significant amount of time in this general area campus, this was still a beer brewery. So I guess we're changing over from a fountain of beer to a fountain of knowledge as Google has moved here, or a fountain of information on the web. What I'm going to try and do today is talk a little bit about one of the studies that my PhD student who just graduated, Esther Kaufman, mainly did, which was looking into language and how people are able or not able to put together certain things that they're trying to find out into language, in specific natural language. And I'll be telling you more about this study essentially throughout the whole time. Actually, I was never told how long this should be. About an hour. Okay. Before jumping into this, maybe let me just quickly tell you what I'm doing. I'm doing essentially two things. I'm looking on the one side of machine learning. Different areas within machine learning that I'm looking at is relational machine learning, so trying to extract knowledge from relationships between entities rather than just attributes or features of entities, and I'm glad to talk about that more. We're doing stuff with banks where we're trying to do some fraud detection. We're looking at temporal data mining and some other stuff with that. We're also looking at probabilistic reasoning to do NMR analysis, nuclear magnetic resonance spectrometers analysis. On the other side, I'm doing stuff in the semantic web, and that's much more what's prominent to this talk here, whereas I take the semantic web as a very open specification, so I don't say it has to be description logic, but it's actually the attempt of putting semi-structured information out there that can be processed in a machine way. There's essentially three areas where we have been focusing on. One is we've been trying to use a combination of inductive and deductive reasoning to get somewhere. This is our iSparkle work that we've been doing. Sparkle is the general query language to query semantic web data. We have been doing some stuff on query optimization, where we have a recent paper just now in VLDB where we show how Sparkle queries can be optimized much better if you have the appropriate storage structures. And last but not least, we've been interested in finding out how people can actually get access to this information. Now, just to kind of set the stage, how many people here know what the semantic web supposedly is? I mean, okay, I see some people. Let me just give you just a very short kind of idea or notion of this. This is another slide that I wanted to put out because I thought you guys definitely know what the web is. I don't need to tell you guys. The idea behind the semantic web, or the original idea, was that rather than putting out pages of information, what you do is you put out different assertions at different places. So different statements about whatever you want to make statements about. So, you know, the easy thing is, you know, you have a penguin called Pingu. I don't know whether you know Pingu. Pingu is a very popular children's TV show character here in Switzerland. And I see there is a font problem here. This should be an existential. So there exists an X where penguin X, that implies that X is a bird. And then we may have a second knowledge base, which brings up another thing that doesn't seem to work with the fonts. So there exists a Y where a bird Y implies that the bird can fly. And obviously what you see is you have two different knowledge bases, two different places. You get conflicts, et cetera, et cetera. But that's the general idea of the semantic web. You have assertions out there rather than just text or rather than just HTML. And you're trying to exploit that, take that data together, and make some statements. OK. So the logic of the semantic web, or at least the proclaimed logic of the semantic web, is this thing up here, which is something called OWL in its absolutely unreadable XML iteration, or for human purposes, almost unreadable. So it's a description logic. You have classes. You have relationship between classes. You have properties of classes, and relationships between these things. So what you have up here is you have a city, a class city. It has a subclass capital, which is a subclass of a city. You have a city population, which is a property that has a domain of city and a range, in this case, of a float, which is probably not quite necessarily correct. It probably should be some type of integer rather than a floating point. You rarely have a 0.3 inhabitants in a city. But anyhow, so you have this model which very much looks like a object-oriented model, and you can do some reasoning about it. And there is a query language that goes along with it, which is, you know, your standard SQL-like query language, only that it doesn't have a from statement because you don't query from a database, but you query from the collection of asserted statements that you have. People are not really good at looking that way. People who seek information or try to accomplish something are not really good at putting together these statements down here, right? So SQL is not their game. Or said differently, and that's essentially what was driving our research here, how can we bridge this huge gap between what semantic web researchers, or actually any kind of database has, namely this logic-based, knowledge base or database on one side, and people who are at least ill at ease, but usually incapable of putting together formal logic statements. Actually, there is plenty of research in psychology and other areas that shows that we're really not good at putting together logic. There is a study by, what's his name, Anselm Spurry, early 90s, who used MIT undergraduates. He had an information retrieval system where he had people either assemble Boolean logic or use some graphical-based query system that uses Venn diagrams. And even, you know, MIT undergrads who are supposed to be brainwashed with logic were not able to do this, you know, well if you gave them the Boolean logic statement as compared to when you gave them kind of Venn diagram-like graphical representations. So we can assume that if MIT undergraduate students are not good at this, and I guess I can do a little bit of MIT bashing since I'm an alum, even, you know, if they are not comfortable at doing this, why should the general public? So how can we bridge this gap? That's kind of the underlying question that we're trying to look at. So what are possible answers? Well, one possible answer is natural language. It might not be the first possible answer that you have been thinking about. The other possible answers, I mean, what do people do with databases today? I mean, the standard thing that people do with databases today is, you know, query by example. Query by example is relatively straightforward, right? You have these forms. These forms kind of represent in some way your database structure. People fill out whatever they know. They hit return, and they see what kind of results they get. So query by example doesn't work if you have large or semi-structured databases because the structure is not in first normal form. So first normal form would be that every attribute is a primitive data type, right? And if you have the attributes not being primitive data types but aggregated data types, suddenly your query by example statement has to refer to objects which are again complex objects, which are again aggregated objects, et cetera, et cetera. And query by example suddenly becomes a very complex and complicated proposition. So other things you could do is graphical user interfaces. And this is actually something that we compare against later, so that you would have objects and you have relationships between objects, and you have people draw, you know, boxes and arrows and stuff like that. Although I want to say that we, as computer scientists, or at least I'm assuming you're at least computer science, you know, related or somewhat have been heard something about computer science in the past, we've been all kind of gently brainwashed into this idea that these boxes and arrows have certain semantics and they have certain meaning. And it's not necessarily true that the general public is actually comfortable with dealing with boxes and arrows. There is a nice paper by David Karger and MC Schreffel about the fallacy, the pathetic fallacy of using graphs to represent data. Because they are a good KR, a good knowledge representation, but they're actually not a good representation of that data for human consumption, for average human consumption. Okay, so one alternative would be natural language. Natural language is an alternative because we have all been learning it for the last, you know, however many years you're here. We have been learning natural language, right? It's something that you've been using day by day. It's something that most of us are plus minus comfortable of expressing our desires in. I'm saying plus minus, but since this is not a psychology talk, I'm not going to focus on the minuses. As a matter of fact, there is an argument by somebody named Turtle who developed a system to actually front end to some of these legal databases that have legal cases in it for the US, that lawyers and people who do research for lawyers are more more comfortable at putting together natural language queries than Boolean queries. I have to say that Turtle did the study in '94. You know, you could argue time has passed since. People have learned differently. The web, and definitely querying on the web, has not been as prominent in '94 as it is today. So people may have changed their habits. However, natural language is a mess. It is linguistically ambiguous and variable. Oftentimes, we develop whole protocols in conversations around how to actually make clear what we actually mean. It is often seen that there is a certain adaptivity barrier, and NLP systems are usually tied to certain domains, and in order to work well, there is a whole lot of work that needs to go in if you want to have them work on another domain. There is a number of quality of performance issue, be it speed, be it also quality of answers. And in addition to that, we're not yet done, there is this thing called the habitability problem. So the worst thing you can do with somebody is put them in front of an empty prompt. While granted, you know, when you put somebody in front of a Google search screen, they have been socialized into knowing what to put in there. If you put somebody in front of a prompt and say there is some knowledge base behind a query, they'll go, well, what can I ask? What can I not ask? What is it actually that I can type? And there has to be a certain understanding in their mind as to what the system can do and what the system cannot do. So users need to understand what's possible in order to actually know what to write. Last but not least, there is obviously this question as to, is NLI, is this whole field of natural language interfacing to knowledge bases or to databases, completely redundant, given that we have been in a generation of, you know, search by keyword and clicking. Started by that, we started off with this question that, is it really this way? And is natural language useful? Or do casual end users, and we put a big emphasis on that, casual end users find natural language query systems to, in this specific case, ontology-based data repositories useful? Although you could probably drop the ontology base away. I don't think it's actually necessary to the experiments that I'm going to show you. So how do we go about doing this? So this is the point where I'm going to try to tell you a little bit about the setup. What we did first is we were thinking of how can you think of query languages and of structures of query language that people may want to use. And we came about this theory that comes from sociology called structuration theory. Structuration theory, as authored by Anthony Giddens, says that in order to be able to act, people need a structure. In order to be able to make meaning of things, we need some type of structure. Without that structure, you know, everything we encounter is just symbols that have no meaning. It's the structure that lets us put relationships between those signals and actually make us understand what these relationships between those signals and what the signals mean. So that's one end, or one side of the structure. Structure also has another side, which is, whilst it enables us to make meaning, it also prevents us from seeing other aspects in the data. So it's also constraining, right? If I happen to look at my laptop and what I see is a computer, I will most probably not use it, you know, to swat flies. if I want to, if a fly bothers me. It's because it's not in this set of concepts. And all of those who've seen this movie, The Gods Must Be Crazy, where a Coca-Cola bottle is being thrown out of an airplane over the Namibia desert, and a tribe of Bushmen picks up this Coca-Cola bottle, and they put this Coca-Cola bottles to lots of uses, none of them which is fill it up with a fluid. You know, our structures and our knowledge structures and our understanding actually form what we see in things and how we use those things. They enable our action, but they also constrain the actions that we can do. So structure is good because it allows us to do stuff, but structure is also bad because it prevents us from doing other things. So how can we use this to operationalize our question that we had before? And what we did is we said we should look at languages or query languages of different degrees of structure or formality. And so what we said is, in essence, there is this kind of spectrum between highly formal language on one side, and I just put Sparkle here, put first-order logic here, put SQL here, put Boolean logic here, put whatever your favorite formal language is here. And on the other side, you know, somewhere is natural language. Natural language has structure. You know, if I would say it doesn't, any linguist who would come by would come and shoot me. There is definite structure in natural language. But at some other end, there would be a completely unstructured language, query language, that we did not look at. But what we tried to do is we tried to imagine what are different query languages on the spectrum between highly structured formal logic, which we have a strong feeling about that your casual user would not use it, and on the other side, a query language with as little structure as possible. By the way, I have a strong feeling about that this doesn't work. You guys have real data on this. We don't. The last publication that I know of that kind of characterizes search query engine data gathered by search engine is by Spink et al. It's a, what is it, 2001 or 2002 publication. And they, I think, looked at query or real queries gathered from either Lycos or one of these query engines. And they saw that only 1% of all queries actually had Boolean statements in them. And of those, about half the Boolean statements were incorrect. Yes?
One comment, I would say that web search queries are actually off your scale there to the left. They're less structured than natural language.
Yes, so I may want to point out that this is not good here. So the natural language is not the right end. Oh, sorry, I should repeat the question. So the question was, he wants to point out that web queries or web searches are actually off the scale. And my answer would be, yes, you're right. The misnomer there is that I put natural language at one extreme, which it is not. I would say, you know, you guys or keyword search. Let's call it keyword search. Is somewhere here, and then there is something that doesn't have structure at all, which I don't know what it means. But you know, there could be something that doesn't have structure at all. There is a certain structure in the way you guys interpret when I enter keywords, or any search engine interprets it. So there is structure there. There is an assumed structure there, at least from all the users when they tell me, oh, I do this and that. And sometimes I don't understand what that would actually mean, the way search engines process this stuff. But there is definitely structure there. There is less structure there than natural language, absolutely. And you'll see that what we're actually going to do is we developed 4 different search engines which have different degrees of structure based on the same data set. We gave people the same tasks, using all 4 systems in different orders. And we looked at which the systems did they perform best. And the system on the far left here, this thing called NLP-Reduce, is the least structured system. It will actually take whatever you enter in terms of words. So for example, if I'm staying with this US geography data set, which is actually the one we use to do our experiments, you can put things in like cities, size, Georgia, or size of cities in Georgia, or what are the population sizes of cities in Georgia. And it will process whatever, and will try to make best guesses about what you're actually doing. So that's NLP-Reduce. And we called it NLP-Reduce because we tried to use as little NLP as possible. We actually tried to use, actually, we didn't use any NLP, would be the right word. And we tried to just to do a best guess on what the answer was. The next system over is called Querix because it actually expected correct English sentences. So it was parsed with a NLP parser, the Stanford parser. And I'm going to explain how each of the systems works in the next few slides. This is just kind of to give you an overview. So here you'd have to enter things like, give me the population sizes of cities in Georgia. Or what are the population sizes of cities in Georgia? Here you need full sentences. Otherwise, Querix would come back and say, sorry, it does not compute. We also had a system called Ginseng. Ginseng is a system that actually only, or was only able to interpret a small subset of English language. So it looks English. It's actually a formal query language. And last but not least, because we did not want to confront our end users with real natural language, with real formal queries or Boolean queries or any type of formal logic, we confronted them with boxes and arrows. And we had them draw relationships within things with something we called Semantic Crystal. So let me do the following. Let me walk you through each of these systems. And then afterwards, I'll explain you what kind of experiments we did. And to see so how did people actually react to this? Because I think that's the interesting part. So the systems are throwaway systems, right? We just built them to run this experiment. They are by no means the best NLP systems. They're by no means the best query systems. They're really throwaway prototypes to run this experiment. They were specifically developed for these experiments. So NLP-Reduce takes keywords in any sequence, in any form, will absolutely ignore whatever order these keywords are being used and have been entered, and will try to make the best out of just taking these keywords. What it will do a stemming of the input questions. It will then try, input words. It will then try to take each of the words and find them in the knowledge base. So if you have cities, it will try and find cities in the knowledge base, and it will probably find it in a class that's called cities. As we saw before, there is a class called cities. It will look for Georgia. It will not find Georgia in the class hierarchy, but it will find Georgia as an instance of state. And that way, it will try and find each of the words that it can find. Thereafter, it will try and find connections between those words within the knowledge base, and it will try to do that by having those connections being the shortest possible in the graph that's essentially being put up by the knowledge base. And then it will try to take these connections and turn those into a logic query. So how does this look like? You enter your question, and you get the answer below, and some type of logic query is being generated. Specifically, the user enters the question on the top left. Even before you take the knowledge base, you index it so that you know where all the words are in the knowledge base. You then reason about it so you can get to the closure, to the logical closure using a reasoner. You take all the words that you have. You build up all the synonym sets, so you have all the synonyms and so forth using WordNet. So we have town, urban center, metropolis, municipal, etc. And that way, we have a lexicon, which is the lexicon of words that we know that we can use, that we can interpret. When the user now enters a question on the top left, we use that question, that queries, for example, how big are the cities in Georgia? We port the stemmen, big B city, Georgia. And we now try to find those in the triple store, which is enriched with the synonyms and the inferred statements based on the logic. We match them against these. We try to find some type of minimum spanning trees that connects all the properties that I found. Put together the logic query. in this case, select star where city has population some value, and city is city of Georgia, so it's in the state of Georgia. And then we run this query and return the results. Okay. So this is very simple, very simplistic. This is nothing you write PhDs about. You probably don't even write bachelors about this. Okay. What's the next system? The next system is Querix. And what we found when building NLP-Reduce is that in many cases, those connections are quite ambiguous, or the relationships between the words that get entered in a query and which word in a knowledge base it should be are ambiguous. It's not clear what you actually mean. So give me the biggest city in the US. Well, what do you mean? Do you mean by area? Do you mean by population? What's biggest mean? Okay? So we built a system that's a little bit smarter in terms of linguistics. It parses full English sentences. It does also do a synonym expansion of the knowledge base. It does full question parsing, and then tries to find the triple patterns it can find in the parsed sentence in the knowledge base to generate the SQL, the Sparkle query. And when it hits ambiguous questions, so like, what is the biggest state in the US, it will come up with a question box that will say, and I'm sorry, this is probably too small to read, biggest state means highest value of the property state population density, or means highest value of the property state area, in which case it would be Alaska, et cetera, et cetera, et cetera. So it would ask you back, and that's why we call it Querix, because it's a little bit like getFX. I don't know how many of you know Asterix and Obelix, which is this druid that all the villagers of that village go to whenever they have a problem, and he gives them an answer. Okay. So let's see how this works, just very quickly. Again, from the bottom, I'm not sure this is nicely, no, this is not as nicely animated, so I'll have to step in here. So we take the knowledge bases that we have, we take a reasoner, we read it in, we reason about it, we do a WordNet expansion again on the synonyms, etc., and store everything in this extended knowledge base. Then what we do is we take the query that's entered and we analyze it using a full NLP parser, in this case the Stanford parser. And then what we have is a sentence structure. Let me show you in detail what that means. So we take, again, a similar question as we had before. What are the population sizes of the cities that are located in California? We get a parse tree that looks something like this, right? What are the verb, the population sizes of the cities that are located in California? We only take the leaves with the types, what type of word it is, and we throw away the tree structure. And we end up with this thing. What we now do is we take the different words and we expand them with their synonyms. So population sizes, inhabitants, citizen, number, magnitude, measurement, etc. Cities, town, metropolis, urban center, municipal, etc. So that's what we do on the one side. What we also do is we try and find certain triple patterns. So patterns are three things that are in relationship to each other that are often found in questions. So we have something like a verb pattern. That's the green one here. What are the population sizes? We have a preposition pattern, population sizes of cities. And we have a WH pattern, so like a question, like one of the W words, right, that are located in California. What we're now trying to do is we're trying to construct all the triple-based relationships that we can construct from these things that we found here. And we're trying to match them against the triples which we found, so the relationships that we found in the knowledge base that have these words in them. So let's go to the knowledge base, and we found all these relationships that have at least one of those words in them that are in the query. So we have R, something like a relationship between a domain, which is a city, is city of. There's a relationship between is city of and R, and a range state. We have the word population size, which actually shows off in a synonym of has population. That's another property that connects a state or a city with some type of number. We have cities, which actually shows up in two contexts, like a city is a city of a state, and a state has a city, which is a certain city, and are located, etc. And now what we're trying to do is we're actually trying to match the colors above with the statements below. And the way this looks like is as follows. You take, for example, the screen statement, and you see that it fits very well with this domain state or city, has population, and range number. And that's what we do with each of those bubbles that we found above, the possible triple patterns in the question. Well, the red pattern actually matches the same triple, the same relationship between a thing so having a certain property and another thing. And the blue one actually matches against those two. As a next step, we throw away the ones we couldn't match. And we're saying, OK, if these are the remaining triples, we need to be able to hook them up in some way, right? We need to be able to join them. Otherwise, we're getting, all the states that have a certain population. So we need to be able to hook them up in some way. So we're looking at the domains and ranges that match so we can do joins. And in this specific case, we're ending up with this relatively simple query that says we have a city that has a certain population, and we can join the city with is located in California. And we get the population size. OK. So that is a system that is a bit more elaborate. It is the closest what we built to a full NLP system. Still a very simple system if you compare it to other NLP systems. OK. The next thing is Ginseng. Ginseng is a system that essentially takes the KB, the knowledge base, or the set of assertions that you have, and compiles all the possible questions that you could ask. I mean, this sounds odd, but in some sense, it is doing that. It takes the knowledge base, it extends it again with synonyms and antonyms, and then compiles a grammar from the knowledge base and combines it with a simple question asking grammar to put together the grammar of all possible logical questions that the simple system could answer. And in that case, once you enter the question, all you do is incremental parsing through your constructed grammar to construct the query that you have to answer. So it's a very limited system. It can only answer the questions that the people who built the original question grammars actually thought of as a question that could be possible to be asked, but it is being enriched by the knowledge base as in terms of an answer. So what happens is you type along, and you get these drop-downs that tell you how it works, what the possible things are that you can enter. So the system, again, as a diagram, is very simple. You have a simple static question grammar, which is just what is a standard form of a question. You take the knowledge base, and you compile your actual grammar, which you then use to interpret incrementally as people type what is entered. So this is like you're in Eclipse, and you get these drop-down boxes of what the possible methods are that you can call. OK. Last system. The last system is Semantic Crystal. It's essentially a system that allows you to drag and drop together concepts from the knowledge base and draw arrows between them to do these boxes and arrows thing. And essentially what you're doing is you're putting together logical queries. Semantic Crystal looks somewhat like that. So here you have the things that you have in your knowledge base, and you drag them over. And then you have something like this up here, kind of, I'm just enlarging what you have here. So question mark states, that's a variable you'd like to have back. You have a state and a river. They're connected through runs through. It's the Rio Grande, and what states does the Rio Grande run through? OK. So far, so good. I don't think those systems are very exciting in themselves. They're exciting when they're put together in one usability study. So what did we do? we took a bunch of subjects, and we gave each of them the 4 systems to use. We gave each of them a set of questions, and each of them used the 4 systems in different orders, so we get the statistical cleanliness of such a usability study. And we looked how well they performed, and we asked them what they liked. And let me go through that for a moment. So again, 4 systems. The task was they were given 4 questions, and I'll show you in a moment what those questions are. They needed to reformulate them and enter them into the system, find answers. We did a promotion on websites and billboards around Zurich. We got 48 real people, meaning we got almost any profession. I think we excluded psychologists because psychologists make for awful subjects. The reason is psychologists get there is a real reason to it. Talk to any experimental economist. The psychologists have been trained with so many experiments in their training that usually when they're being put in an experimental situation, they're trying to find out where they're being tricked. And they use so many mental cycles on finding out how they're being tricked that their results are influenced by that fact, and therefore they don't make for good subjects. So we didn't use psychology. I think that was the only exclusion criteria we had. We have completely evenly distributed backgrounds, bankers. Sorry, we're in Zurich, so they come first. Biologists, housewives, musicians, teachers. We had some unemployed people. It's amazing how many unemployed people actually do, experiment hopping, because it's a way to get some additional income. We made sure we didn't just have unemployed people, because that would skew our results as well. We had age between 19 and 52, with an average at about 27.6 years. We took a data set that was given to us by Ray Mooney down in UT Austin. It is this kind of simple database of US geography. It has states, capitals, cities, rivers, lakes, mountains, lowest points, highest points, and relationships between each of those things. And we asked them questions like, what is the area of Alaska? What are the number of lakes in Florida? What states have a city named Springfield? And there is many states in the US that have cities named Springfield. Rivers that run through the state that has the largest city in the US, and things like that. So it's an increasing complexity. And we essentially gave them all these questions with each of the systems. Obviously, the questions were different for each of the systems. So it wasn't like area of Alaska. It was area of Alaska. It was population size of New York. But the questions were of the similar type. We observed the people using Moray. Moray is a wonderful tool. The person sits in another room. You essentially see mirrored what they do. And every click event that they get, so this is a picture of what the subject gets, you get the event. The person moves the mouse. You see how the mouse being moved, etc. You can observe everything, and we annotated whatever they did. The experimental procedure was essentially as follows. They got a piece of paper describing the overall experiment. Then for each query interface in varying order, they got some instructions, a one-pager, how does this work, the system work. They got the 4 questions they had to work on, and they executed them. Then they filled in a SUSE questionnaire. The SUSE is what's being often called the quick and dirty usability test. It's a test with, I think, 10 questions on a 5-point Likert scale that people answer. How much did you like the system? How suitable did you think was your system to this use? Blah, 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 etc. Then they filled out a comparison questionnaire between the systems. And at the end, they provided an answer to a demographic questionnaire, so we would have data about them. So now it becomes interesting. First of all, average time to fill out the queries. The average time to fill out the queries has a structure that I think is something that we would all expect. It essentially tells us the more structure you impose on people, the longer they will have to fill in a query, right? So we go from NLP-Reduce, which is your keyword-based thing on one side, down to Semantic Crystal, and you see the more structure you impose on people, the longer it takes them to fill out the query. And this is highly significant with the usual t-tests that you would do on such a thing. It is especially interesting that the time between the shortest, which is NLP-Reduce, and the longest is huge. I mean, you know, this is almost 4 times as long that people take when you impose a logical structure on their queries. Now, again, this is time. It doesn't mean how good the answers were that they got. Let me go on here. Second, how happy were they with the system? So that's the Seuss questionnaire. Essentially is the higher the number, the happier people with the system. And what comes out here is that, interestingly enough, they were happiest with Querix. Remember, Querix is the system that requires you to put in full English. You cannot put any keywords. Actually, they were significantly happier with Querix than with the keywords. Right, this is the year 2007. This is not 1994 like Turtle. They were happy. They felt much more comfortable with the system, entering full sentences. This is not what I would have expected. I would have expected they're happiest with, you know, keywords because it's the least work. They were least happy with Semantic Crystal, again, because it puts the burden of the structure on them. But it seems, sorry, one more thing. The difference between Ginseng and NLP-Reduce is actually not significant. So it seems as if structure makes them happy to a certain degree. Now Giddens, you know, would be happy and dance around here, right? He would say, sure, because we all love structure. We have been taught to use structure, and we've been all taught to use language structure since the age of 1, or whatever it is. Is that a question, or?
Yeah, I have one question. It seems to Querix, though, you have another dimension. It has interaction in it.
Yes.
I mean, to me, that could be an explanation for this.
Yes, it actually, to a certain degree, is. And I'll get to this further down, but the qualitative answers that we got was, or one of the qualitative answer was, they trusted the system more that was having an interaction with them. And since Querix had this type of, is this what you mean, they trusted it. But that was an element of trust. The Seuss questionnaire was fidgeting apart the trust issue, though, from which system were you the happiest with, kind of which did you find the most comfortable and easy to use. And I would argue keywords are easier to enter than full sentences. I mean, I know how it hurts myself when I, yes?
But when the users filled out the questionnaires, they already knew the answers, or they were happier with results from one system as opposed to another system. So that's what usually you take into account, as well, or what the users take into account.
No, they actually did not know the answer. So they had each system, and after the system, they filled immediately out the Seuss questionnaire. So not all, so some of the subjects had Querix before they had NLP-Reduce, and some not. So there are different orders here. So that effect gets equalized out.
But at least the users had some sort of idea about the results.
What the result is.
Once they used the system.
That is correct. They did not just answer the question. They got an answer from the system. Yeah. And so they may or may not have been happy with some of the systems or not.
Because of the results.
Because of the results. So, yes. We also put out a pure comparison questionnaire. You know, which interface did you like best? Which interface did you like least? And there you have the Querix again that was winning. And there they actually, so this is why I didn't answer, you know, because I said the question will come later. It was very clear here that what they liked best about Querix was the fact that they were having an interaction. It wasn't the one-shot deal. So here I would say, yes, you're completely right. I'm not really sure on the other thing, on the usability, on the pure, which system did you, which kind of query language did you like best? Actually, we did ask them about the query language itself as well. So this will come out in a minute. Oh, here's the query language. Sorry, it's on the same slide. I should look at my own slide. So we also asked them about the query language. Now, you could argue it is not completely orthogonal from the interaction experience they were having, since they were using this language in an interaction experience. But again, I mean, the difference between the 60% that we have here and the 18% who liked the other one best, there is a certain strength here. People seem to like natural language, or casual people seem to like natural language. I don't know why, but they seem to like it. There seems to be something in it that people like a lot. And it would be dangerous to just discard this as you had nicer icons on one system versus the other. They really genuinely seemed to like the fact that they could enter full sentences. Obviously, the one they liked least was the formal one, even though some of them really liked it. I mean, I was surprised at this number that 14% or roughly 15% actually liked the formal language most. This is not the computer scientist we had in the test, and it is not the computer linguist we had in the test. I'm used this as a singular. I think we had one computer scientist in the test, and we had one computer linguist. So some people actually liked the formality of putting together boxes and arrows. Yeah, no. So this is right. This is the interface. So but they liked the fact that they could put drag and drop things together. Yeah, if you look at the language, it falls to a very, very low number. And obviously, almost everybody dislikes this most. OK. Let me look at some of the dependencies that we got. If you looked at the dependencies between the other variables that we gathered, between the SUS score and what the relationship was, each additional second spent actually decreased their happiness by 0.06, right, their SUS score. So that would tell you want to be quick. Better knowledge of informatics, computer science, or whatever you want to call it, made them happier. It's interesting. I never associated knowledge with computer science make people nicer in terms of how much they like a user interface. But it seemed that they were feeling more with us as this is a difficult task to do. I don't know. The system that was tested last always obtained a slightly higher SUS score. Geez, I'm done, right? I can now be happy. Anything else that we could know did not factor in significantly. So it wasn't the success and failure rates. It wasn't the order of the queries. It wasn't how much you knew about linguistics, whether you knew English, what your gender was, age. Nothing of that influenced your kind of assessment of the SUS score. How happy were you with the system, which surprised us. Let me go into the qualitative statements, and that was, I think, very interesting. Because it kind of highlights some of the things that are a little bit more salient, but obviously they're qualitative answers. They liked simplicity in both NLP-Reduce and Querix. They didn't like the presentation of the results in some of the systems. Yes, we should probably control for this. If we would run this again, we would make every system look exactly the same down to the last pixel as far as we can. They found Ginseng simple because of the drop-downs, because they didn't have to guess. So how can I enter things? What can I enter? But they found it too restrictive. So this is, again, structuration theory at its work and so showing up as its best. They liked the graphical display. They liked the fact that they could actually see what they were querying. So this, I don't know whether I recall this picture of NLP-Reduce. where you could kind of get a picture of the domain you were querying. Here it is, right? The fact that you could see what was in the, what's in the box that you're querying. They really like that. The question is, how much does this scale, obviously? And this is a very small knowledge base. It probably wouldn't scale very well to very large ones. But obviously, they didn't like the logic because it was too laborious and it was too much work. Now, coming back to the languages rather than to the interfaces, let me just point out a few things that are of interest. They like to use keywords, and they like the fact that they didn't need to think when they were doing that. On the other hand, they complained that the query language was unclear. Again, I think this structuration theory message kind of comes back up here. I can use my language. It's simple to use. It's clear language. Again, they like the fact that they could put together natural language. They didn't like the fact that they had to put in full sentences, right? And nobody said that people are consistent in their answers. They like Ginseng, the drop-downs, because it was assisting the suggestions that they would get, but it was too restrictive. They like the playfulness of the boxes and arrows, but it was too much work. Okay. Now, what I talked to you so far was people's personal impression. What's almost as interesting, if not more interesting, is actually how good were they in terms of fulfilling the task. And there is two things. There is how good did they think they were fulfilling the task, and how good did they actually fulfill the task. So their perceived success rate was actually lowest with Semantic Crystal, with the logic-based, and highest with the language-based. Probably strongly influenced by the fact that they perceive the fact that I'm having an interaction with the system as a signal that I'm doing right. On the other hand, when you look at the real rates, so this is not, we asked them, did you get the answer? Yes, no, right? They could check it. If we looked at whether they actually got the right answers, NLP-Reduce, the keywords, were actually best. Now, right, this is striking. So this is the perceived one, where NLP-Reduce clearly and significantly loses against Querix, and the real one, where NLP-Reduce not quite as significantly wins against the full sentences. Now, note something that happened here, and that's why it's non-significant. Ginseng, which is this formal language hiding out as natural language, actually won over Querix here. And the reason is, when you fired off a question, it was answered correctly, because you couldn't enter an incorrect, you could enter a question that would get a wrong answer because you asked for the wrong thing. But whatever you would compose, if it looked right to you, in most cases, would actually produce the right answer. You couldn't enter a nonsensical query that wouldn't be interpreted right. So at least the step from the interpretation step, from English to the logic question, there was no ambiguity in that. Yes, I talked about that. Now, these results are not quite as significant as the rest. Okay. So let me summarize these findings, because I think there is some quite interesting stuff there. Casual end users seemed to have preferred natural language interfaces with some full English elements. So, don't throw away the idea of natural language. People are comfortable with it. Full sentences were perceived to provide more freedom and are more natural than keywords, which is mind-boggling to me that somebody would say something like that. But that was a perception. NL seems to be leading to a perception of correctness, especially if it is put up into a conversation. Is this the answer you were looking for? We didn't have this in, but I'm sure if you would have a conversational interface, people would rate it even higher. Graphical display of what's available or some type of notion of what's available is helpful because it allows you to understand what is searchable. And what's probably best would be to develop some type of combined interface that allows you to use fragments of natural language with fragments of keywords to actually exploit the advantages of both those elements. Now, this is the point where I'm starting to hypothesize. OK, I'm done. Thank you very much. And I would be very, very happy to entertain questions. Yes?
What a priori knowledge did the users have about the mentioned systems before doing the experiment?
A one-page write-up, which essentially explained what do you need to enter.
Okay, so they knew that they might construct certain queries with the natural language and the others with the
So
limit.
for example, for Querix, it would say you can only enter full English questions, and it has to be a question, so it needs to start with one of the W words, right? Where, what, or H, right? How much or how. And the system will only accept questions like that. For NLP-Reduce, it was you can do whatever you want. You can enter full sentences. You can enter keywords, and you hit return. For Ginseng, it was you can only enter what the drop-downs allow you to enter, etc. It was a one-page maximum per system. In most cases, it was like half a page.
Thank you.
OK, so let's thank the speaker. And we will take more questions afterwards. Those who want to stay longer, here's another full hour to take questions in a smaller group. OK, let's thank the speaker.
Thank you.